Okay, so this is where we left off talking about how the operating system and the CPU make everything appear to be working seamlessly, okay? Every keystroke, every mouse click, and each signal to the printer and from the Blu-ray drive creates an action, or what we call an event, okay, in its respective devices. So like the keyboard, the mouse, the Blu-ray drive, the printer. So once this event is created, the operating system responds to it. Okay? Sometimes these events occur sequentially, such as when you type characters one at a time, but other events involve two or more devices working concurrently, such as the printer printing while you type and watch a movie. So although it looks as though all the devices are working simultaneously, the operating system actually switches back and forth among processes. So assume you're typing and want to print. When you tell your computer to print your document, the printer generates an interrupt that tells the operating system that it's in need of immediate attention. Okay? An interrupt is a computer science term, right? Every device has its own type of interrupt, which is associated with something called an interrupt handler. And all that is a special numerical code that prioritizes the requests. So I know this is kind of complicated, but I'm just trying to explain to you sort of what's going on behind the scenes, because it's important for you to understand how these tools work. Okay? So these requests are placed in the interrupt table in the computer's RAM. Remember, the random access memory. The operating system processes tasks in order of priority. And we call this entire process preemptive multitasking. Right? So when the operating system receives the interrupt from the printer, it suspends its current activity and puts a memo, okay, I'm saying that with quotes, like a little note to itself in a special location in RAM called a stack. So that's kind of what I was trying to show you here. This is like one of those little receipt holders. You'll see them at restaurants sometimes, or antique stores maybe. Okay. The way your computer is working is, okay, so right now, say it's happily moving along and, showing this PowerPoint presentation, running the Screencast-O-Matic screen capture software, whatever else happens to be going on in the background. Okay, so, and I decide, hey, right now I'm going to print this slide. So I send a press print, okay? I send a print request to the operating system. The operating system says, okay, hold up. So it pauses in its work of the screen capture software and in the PowerPoint presentation, and it writes a little note to itself, and it says, okay, I was working on the PowerPoint presentation and I was working on the screen capture software. And it sticks that note in a stack. Okay? And then it goes to work on the printer request. So now it says, okay, now I'm going to print this slide that she just asked me to print. All right? Of course, this is going on behind the scenes, like incredibly fast. So fast that we don't really even notice that it's actually, stopping what it's currently doing, writing its little memo out to itself, and then going on to handle the request you just sent it, which in this case would have been to print this slide, okay, like this slide that I'm working with. Okay, so puts the memo in a special location in the RAM called a stack. The memo is a reminder of what the CPU is doing before it started to work on the printer request. The CPU then retrieves that printer request from the interrupt table and begins to process it. On completion of that printer request, the CPU goes back to the stack, our stack right here, retrieves its memo that said PowerPoint and screen capture software, and returns to this task at hand, okay, until it receives another interrupt. It gets interrupted again. Then it's going to again create the memo, put it in the stack, process the interrupt, and then come back to read its memo, and then come back to what it was working on. And all of this is happening seamlessly. That's what just blows my mind. Despite, I know how this stuff works, but it's still crazy to me how blazingly fast this stuff is happening. So the operating system also coordinates multiple activities for peripheral devices, such as printers. When the processor receives a print request, it first checks with the operating system to ensure that the printer is not already in use. Okay. If it is, the operating system puts the request in a temporary storage area called the buffer. I know there's a lot of terms here. I apologize, but just focus on the general idea, not necessarily on the terms, okay? The print request waits until something called the spooler indicates that the printer is available. And all the spooler is a program that helps coordinate all print jobs that are being sent to the printer. Okay, so I'm sure we've all seen this before. Okay, you send something to print, and we're used to instant gratification. If it doesn't start printing, we're upset. Why is it not printing? So we click on our little printer icon that's usually down in the bottom right-hand corner, and we look and see why our stuff's not printing. And we'll see, oh, there's an error here. Okay, so whatever else Matt has sent to print, none of that's going to print until this is resolved, canceled, deleted, however Matt chooses to resolve it. Okay, then it will move on to the next thing in the queue. And if you look at the dates, the timestamps here, okay, these are sent to print like 15 seconds later, okay, and then 19 seconds later, Matt sends whatever this is here to print. So it knows, okay, that's the third document in the queue. All right. It goes in order. It's fair. It treats everything as equal and fair, and it goes in order. Excuse me. Okay. So as the operating system coordinates the activities of the processor, it uses RAM as a temporary storage area for instructions and data that the processor needs. The processor then accesses these instructions and data from RAM when it is ready to process them. The operating system is therefore responsible for coordinating the space allocations in RAM to ensure that there is enough space for all of the pending instructions and data. Okay? Once the instructions have been carried out, the operating system then clears those items out of RAM once the processor no longer needs them. Okay, it has to do this because RAM is a very limited amount of storage space. It's not meant to hold a tremendous amount of data or information. Okay, so it needs to clear items out. Once they've been completed, they're moved out of RAM. All right. The OS is a busy person, huh? Sorry, I always refer to these machines as somewhat human. I don't know why. Okay, so like I was just saying, RAM has limited capacity. When there isn't enough room for the OS, it borrows room from the hard drive. Okay, this whole process is called virtual memory, and it's not a good thing. Okay, when more RAM space is needed, the operating system swaps out data or instructions that have not been recently used and moves them to a temporary storage area called the swap file. Okay. If the data or instructions are needed later, the operating system swaps them back. And this whole process is known as paging. Okay, again, don't focus on the terms, focus on the process itself. Okay. So if you have this happening, if sometimes your computer will give you a message telling you it's using virtual memory. It might even tell you virtual memory is full. You definitely need to increase the amount of RAM on your machine, which is actually very simple thing to do. So don't let that scare you if that happens. All right. So each device that's attached to your computer comes with a special program called a device driver. And this device driver facilitates communication between the device and the operating system. So if you are running Windows, I'm sure you've seen this when you plug in your flash drive or some new device you've never plugged into your computer before, it's installing the device driver software. Okay. The device driver translates the device's specialized commands into commands that the OS can understand, and vice versa. So it's like a translator in a way. Devices wouldn't function without the proper device drivers because the OS wouldn't know how to communicate with them. All right. So without this device driver acting as like a middleman or a translator, your machine wouldn't know how to save files to your external hard drive or to your flash drive, or it wouldn't know how to use your webcam that you plugged in, okay? Because they wouldn't be able to communicate with each other, and they need to be able to communicate. So that's why we have device drivers, okay? Most devices come with the driver already installed, as far as if you're running Windows, okay? And the devices with included drivers in Windows are called plug-and-play devices. Plug-and-play, or PNP, right there. We love acronyms, don't we? Is a software and hardware standard designed to facilitate the installation of new hardware by including the drivers in the operating system. Plug and Play lets you plug a new device into your computer and immediately use it. Again, examples would be a flash drive or a mouse or a webcam, game controllers, okay? Sometimes you might have a device that is so new that the drivers aren't yet available automatically in Windows. So if that happens, you'll be prompted to insert the driver that was provided with the device, or you just go and search for it on the internet and download it. It's really simple, and you'll be able to find it, okay? So for programs to work, they have to contain code that the CPU recognizes. Rather than having the same blocks of code for similar procedures in each program, the operating system includes the blocks of code called an API, or an application programming interface, that application software needs to actually interact with the CPU. So to create applications that can communicate with the OS, software programmers need only to refer to the API code blocks. APIs prevent redundancies in code and make it easier for developers to respond to changes in the OS. Software companies also use APIs to give applications and software suites a similar interface and functionality. So I'm going to stop here, and in the next in part 4, we're going to be talking about the boot process. See you in a bit.